This problem refers to taking into consideration that electrons can also behave like waves. Read the problem, understand the question, think about a solution, work on that solution, and then compare that with the answer that will be described shortly. As we can read in this problem, we are talking about very small particles that are looked under a microscope, an electron microscope. And it refers to the wavelength of light that is required to see those objects. Assuming that we take into consideration the laws of diffraction that says that the object that can be seen has to be larger than 1/2 of the wavelength of electromagnetic radiation that is being used. And we also have here the speed of the electrons. So the plan would be, number one, to use the de Broglie equation to calculate the wavelength, and the equation for that is given on this slide. We need to dig out constants if they are not provided, and we need to keep an eye on the units that we are going to be using. And finally, we are going to divide the calculated wavelength by 2 to figure out the size of the object that can be seen. So let's begin. The expression that we will use for the de Broglie wavelength is lambda equals h, which is the Planck constant, divided by the mass of the particle that is moving at a speed of u. The Planck constant is equal to 6.626 times 10 to the minus 34 joules second. We also need, for this particular case, we are talking about electrons. The mass of an electron is equal to 9.109 times 10 to the minus 31 kilograms. You do not need to memorize these values. They will be either given to you or a table where you can find them will be provided. We also need for this the velocity that is given in this problem at which the electron is moving, which in this case is equal to 3.0 times 10 to the 7th meters per second. So let's replace the values in this expression. Once we have written the values, we also will see that the dimensions that we are using are not necessarily or clearly obviously the same. So one approach to do that is to keep an eye on what joules mean. And 1 joule is equivalent to a kilogram meter squared second squared. Think of physics. Think of the force times space, and these are the units that you will have. And this is equivalent to 1 joule. So if we look at the dimensions that we have here, we can cross out joules and joules, kilograms and kilograms, meter with 1 meter here, and 1 square second, 1 square second. And the final result for that, and we have another second somewhere here that I have not included, this one and this one. So this gives a value of 2.42708 times 10 to the minus 11 meters. So the smallest object that can be seen, as we saw in the problem, is lambda divided by 2, which implies that this size of this object is going to be equal to 1.212354 times 10 to the minus 11 meters. That rounds up to 1.2 times 10 to the minus 11 meters. And if we know our dimensions, we know that this is equivalent to 0.12 Armstrongs. very, very tiny object when we use electron microscopy.